Hey everyone, this is Ainsley from Enigma here. Fred is just getting the Zoom app set up and we should be good to go in a couple minutes here. Nice to meet you all.
Yeah.
Fred,
Okay.
I've unmuted you. I can hear you okay now.
Okay. Thank you.
I'll keep you unmuted and I guess you can mute yourself if you want to.
Yeah. Okay. Thank you.
All right, cool. Hello everyone. I'm going to quickly share my screen. I think we have about an hour. So Fred and I are, like Shreyas mentioned, going to kind of give you an introduction to Enigma, how it works, talk through some of our examples, as well as do a deep dive into how to get started with our API. And then we'll talk a little bit about what we had in mind for what would be cool things to build with Enigma plus Numerai towards the end. And we can get interactive throughout. So if you do have questions, I am not sure if I must unmute you, but I assume you can raise your hand or something like that, and I'll keep an eye on the chat to make sure it's possible. I'm also going to share a link with the group that will just basically be the link to this presentation so that if you want to follow along locally or look at it later or click any of the links, you have the ability to do that. So link is coming now. Oh, no, I don't want to send it to you. I want to send it to everyone. Okay. And I will go ahead and start sharing my screen. Here we go. All right, so everybody should be able to see this now. And I see that some of you are also here with us. Anonymous Koala, shout out. Cool, so like I mentioned, today we're gonna spend a little bit of time going over Enigma, introducing what our protocol does, talk a little bit about what resources are available, for example, sample code, existing demos and prototypes that you can hack on top of. And then we're going to talk also about how to build with Enigma, basically how to get Enigma up and running, what Discovery is capable of, which is our current release, as well as show you how to build a very, very simple application in Enigma to kind of get you familiar with our CLI, with our and with writing secret contracts. And then we're going to spend some time doing a deeper dig into an application we're calling Salad, which basically enables coin mixing on Enigma. And the reason that we wanted to show Salad is because it kind of brings together several more advanced concepts like using a relayer and doing 2 layers of encryption, which is also a useful technique for things that we think may come up with Numerai. So we wanted to take a deeper dive into Salad on this presentation, although it may be something that you revisit later on if all of this is very new to you. So, take from this presentation what's useful, and just know that the rest of it's there for whenever it may become useful to you. And then finally, we're going to wrap up by spending a little bit of time talking about what we thought might be cool use cases for bringing together Enigma and Numerai, as well as like maybe some workshop questions with you. Fred has been thinking through these use cases a little bit, and I think would be glad to kind of handle any initial questions that you have about it. So like I said, I will try to keep an eye on the Zoom. Oh, I won't. Let me see. Sorry, I'm just trying to figure out how to look at the Zoom call while I'm presenting, but I guess I can't. Reuven, I guess, sorry, if somebody just wants to interrupt me if they have a question, that'd probably be easiest for me because I don't know how to look at the, is this it? No, I don't know how to see you while I'm presenting, unfortunately, sorry. Anyway, so let's go ahead and get started, but please, do interrupt me if somebody has a question. One of the reason that Enigma exists is basically to help bring data privacy to blockchain-based applications. All data, as you know, is public by default, which does place pretty significant limits on what kinds of applications can be built, as well as what kind of applications can be built easily. So, for example, there are things like, commit reveals and so forth that I'm sure you're familiar with, which exist to kind of give you some type of data privacy on Ethereum, but are not necessarily the most streamlined or user-friendly way to implement that, and sometimes don't even give you, a true version of what you want, which may be permanent privacy or something like that. So Enigma is basically a secure computation protocol. We enable decentralized applications to compute over encrypted data. Right now, we do the computation on the Enigma network, and we use the Ethereum blockchain to handle verification and consensus. And we can dig a little bit into what that means later on. Discovery is our current release, which is now in a developer testnet with the networked testnet coming very shortly. This sort of stands apart from other solutions in that it's also a permissionless network, so the nodes can be operated by anyone. The nodes are economically incentivized to perform these computation tasks, and we are compatible with Ethereum. We can make Ethereum callbacks from within secret contracts. So the best way to kind of get a sense of how our network works is from the perspective of different stakeholders in the network. We think about this as 3 types of users: developers, end users, and workers. Developers are basically deploying and making these applications. Users are submitting tasks to the applications, and then the workers are the nodes that actually execute the tasks and then perform something at the end, depending on what they are being asked to do. So the developers write secret contracts. Secret contracts are written in Rust. These secret contracts are deployed to the Enigma network. At the same time, a hash of these is deployed to the Ethereum blockchain, which is used to ensure that the nodes are actually computing over the correct data that they are told that they were receiving, and helps manage the payments back to the nodes once they perform their tasks. Users interact with these secret contracts by encrypting data locally using our client library called ENIGMA-JS, and then submitting that data to the Enigma network. We call it a task. And at the same time, again, a hash of this task and it's a metadata sent to the Enigma contract on Ethereum, which, as I mentioned, manages payments and consensus. Workers are basically these nodes which are going to receive tasks based on a stake-weighted lottery from users. The selected worker will execute the task and send the results across the peer-to-peer network. The results are actually just an encrypted, are basically the new state of the contract, which is encrypted. The state delta is encrypted and then propagated across all the worker nodes via a P2P network. And the worker can also submit a result to the task sender and optionally can call a function on the Ethereum contract. And then after the task is verified, the contract releases payment to the worker. So that's kind of at a high level how this works. If you're not already familiar, our worker nodes do use Intel SGX, which is a trusted execution environment, and that's how they're able to perform computation over data that's encrypted to all the participants in the network. To dig down a little bit into the data flow for this system, essentially the user supplies an encrypted input to the network. The worker performs the computation and updates the state, which was an encrypted state update, and then the worker can either return an encrypted output to the user, or the worker can optionally make an Ethereum callback, basically call any Ethereum function and with some data that's dependent on the outcome of the computation that is performed. And then in this case, the user, the encrypted state is then updated, and then, like I mentioned, you have this optional bridge back to Ethereum. So that's kind of how the network is organized at a high level. And we'll walk through that in more detail moving forward. I wanted to pause here and also just share with you some additional links that we have that can help you get started moving forward, probably not right now, but just so you have them in the future. We've put together a list of technical resources here, and this is essentially a list of all of our technical articles, as well as a list to all existing examples that kind of show you end-to-end how to build a secret contract application. This is our forum where we talk about technical questions with the team, and then Discord. This can be useful for troubleshooting, and quick, answers will push you to the forum if something gets too complicated. And then just to kind of set the plan for today, I guess, some things that we were thinking about that you can do with Enigma and Numerai, and this will probably become more clear after we walk through a couple of these sample applications. But one thing that you can do is streamline a commit reveal so that there's only one interaction, and you do that by working with encryption rather than hashing. You could enable more flexible access control to sensitive data. Access control is another primitive that we deal with. And then you can use the fact that we can do private computation in order to make claims about data without revealing the raw data underneath itself. So those are some of the use cases that we had in mind when we started here. And with that, I am going to turn it over to Fred, who's going to basically give you an introduction to our current developer network and walk through a use case with you for getting started. So Fred, I'm gonna stop sharing and turn it over to you.
Okay. Oh, okay. Sorry, I'm just trying to share my screen right now. Can anyone see my screen?
I can see it.
Okay.
You are a bit quiet, though.
You mean my mic is not as loud as Ainsley's?
That is what I meant, but you're getting a little louder now.
Just let me see if I can find the microphone settings.
We can hear you though, Fred. So if you want to just speak up, it'll probably work as well.
Yeah, it looks like the mic is basically at maximum volume. Hold on a second. Yeah, it's pretty loud as far as I can tell.
Fred, I think it'll be okay as long as you speak up. I'll let you know if I couldn't hear anything.
Is it better now?
Yeah, that's great.
Okay. All right. So just a minute. Adjusting something else. Okay. Okay. So I apologize in advance. This is the first time going through this particular presentation, so I might be looking like I'm reading notes, but this is what it is. And just feel free to interrupt me at any time because it might be easier than coming back with questions at the end. Otherwise, I'm going to run relatively quickly through those slides, which basically just try to explain how the Enigma network functions and how to get started. And if my mic is still not loud enough, just let me know. Okay, so this is what the program, this screenshot here is from the Discovery CLI, and this is what it looks like when you use it at first, just for reference purposes. So first of all, the discovery command here is a npm package that you have to download, and it functions similar to Truffle. Actually, it's a wrapper to the Truffle modules that we've used inside of the discovery package. So that's kind of the background on that. So you, at the end of this, we're going to link articles that explain, that give some more background about it and where to download it. But it's essentially an npm package you have to download. And also, in addition to this package, you also need to have a Rust tool belt installed on your workstation. So these are basically the prerequisite. There's actually three prerequisites: the Discovery CLI, which requires Node, a Rust tool belt, and a Docker. And the tutorial articles that we're going to link have some specifics about that. So once you've downloaded all of these and you have them installed, essentially you have this new discovery command, and there's a subcommand called start. And when you invoke this, essentially it starts an Enigma network. This is similar to starting Ganache in the Truffle paradigm. So that would start actually a version of Ganache, which we use as the underlying blockchain, and it will also start the Enigma worker, as we call it, that will be able to process Enigma tasks. What we'll do today, we will build a smart contract and interact with it. Yeah. So a smart contract, sorry, not a smart contract, a secret contract, which is how we call our brand of smart contract, is different from an Ethereum smart contract, and it's written in Rust, the Rust programming language. Reasons for this is that Rust is memory safe. It's got good performance, I guess, subjectively. And it's actually running inside of WebAssembly. It's not running inside of like, yeah, it's not a binary that's running directly on your operating system. It's running inside of WebAssembly. It has a good package manager, and it has a good community, whatever. It's probably a good language to learn for anyone who likes low-level programming languages. It's a very well-made language that can be as low-level as something like C. What we'll build, so the examples I'm going to walk you through right now are based on the MILLIONAIRE'S problem. And the MILLIONAIRE'S problem is just a standard use case that's often used in cryptography to illustrate concepts. And it's essentially using the premise that two millionaires are trying to compare their net worth, Alice and Bob in this case, without revealing the specifics of their net worth. They're just trying to find out who is richer. And we use that just as an example program to show how Enigma works. So here's how the implementation of the millionaire's problem works in Enigma. So yeah, so there's a secret contract that is containing the business logic for the millionaire's problem. And the secret contracts contains essentially an input function in which a number of millionaires can input their net worth, but they input their net worth basically they input it encrypted, and then the millionaire's problem returns the decrypted name of whoever has the highest net worth. So that's what the secret contract does. Right, so you can find this example of the millionaire's problems that we're going to walk through right now, and some more sophisticated examples, some examples that use different functionality of our secret contract APIs inside of our Enigma core library, repository under examples. So just go there and you'll be able to find the reference or source code for this. This is what the millionaire's problem secret contract looks like. Again, that's on purpose meant to be a super simple one. I think it's probably just part 1 or 2, something like this. Okay, so like the next slides kind of focus on the specifics of this secret contract. So I'm just going to walk through the secret contract and kind of give some pointers, things that are important to keep in mind when writing a secret contract. First of all, you have to call this noSTD macro at the beginning of your secret contract. The reason for this is that the STD refers to the standard library in Rust, which is enabled by default when writing Rust programs. And we can't use it inside of a secret contract because we're running inside of WebAssembly essentially, so we're running inside of a sandbox environment that wouldn't give access to the STD functionality, which includes file system operations, in-memory operations, things like that. So you have to enable this macro. Second thing is you have to import the ENG-WASM crate. So the ENG-WASM crate is essentially the API for writing a secret contract. So without this, it will look like you're just writing a Rust program in WebAssembly without specific secret contract features. So the ENG-WASM crate enables your program to actually be a secret contract, and it has specific APIs. So that's kind of similar to the things that Solidity would provide for you to write a smart contract. And ENG-WASM derive is just another part, just another crate that you have to import, and it contains the macro operations of ENG-WASM which is a technical distinction. And also imports Serde. Serde is the serialization library of Rust, and it's being used, for example, to deserialize and serialize the parameters that are used in public functions of your secret contract. So this is an example of a struct that could be declared in a secret contract. You can use struct for things like storing data internally in the state. And I think this does this. We'll see later as we go through the program. But I believe the purpose of declaring a struct like this here is to essentially store the millionaire's value in the secret contract's state. And that's how you'll be able to compute over multiple millionaires in separate operations. So we wrote this whole state management submodule, which essentially allow one to store value in the state and read that value from the state later on in a separate, essentially function calls to a secret contract. And I think this is why this is declared here. And one thing that's noteworthy here is that the types that you might use in these structs that you might use in context of storing things in the state are actual ENG-WASM types, which extend the Ethereum ABI types. So here you see we're using an address as H256, which is kind of confusing because it's a 32 bytes address, which is not the same as the 20 byte addresses in Ethereum. I don't know why. And also we're using the U256 field, which is similar to the uint field in Solidity, for example. So these ENG-WASM types are kind of a Rust implementation of the ABI types of Ethereum. So there's that. Now we also see an example here of two public-facing functions in this contract interface here, the add millionaire and the compute riches. The add millionaire function is what each user will call separately to submit their net worth, and the compute riches function would be what whoever is the arbiter of this will call at the end to determine the kind of the winner. And again, just one thing that's worth noting here is the types. So the types are the same types as what we use for a state struct, those kind of ENG-WASM types, which are effectively ABI types. They're ABI types. Right. Yeah, sometimes, like if you look at some of the other examples, sometimes you would see like a constructor function. So secret contracts support the constructor function. This can be useful sometimes, for example, in the salad program that we'll briefly walk through later, when you want to initialize things and maybe store them in the state right away as the contract is being deployed. The construct function is being called when the secret contract is deployed. So it's kind of a special function that's always being called during the deployment, and you can initialize various things and store them in the states and so forth. But we're not doing this right now because we don't need to. Yeah, so these are just technical things. Like the way that we're implementing our contract here is by initializing a kind of a blank struct called contract, which we can implement a number of things in. And we're just separating kind of our private implementation from our public implementation. So you see, get millionaires is a private function that's being used by the secret contract itself to read the state. It's not being called like externally by dApps. So we're putting it in some arbitrary struct that contains our private implementation. But all of the public-facing functions that are intended to be called by the external library implement the contract interface that we looked at earlier. So that's kind of the distinction. So a contract can have a number of private functions, and with the private function, you're not actually restricted to using these ENG-WASM types. You could use any types that Rust supports, call them internally and so forth. But the public function must be defined in your contract interface, defined for public-facing functions. All right, so this is kind of what this is emphasizing here. Difference between private and public functions. The compute riches function in this case is a public-facing function, and you see that it's kind of an example of a public function calling a private function, right? So you see here it's calling our get millionaires function that we were just looking at earlier, which is a private function which can return anything and have very sophisticated business logic if we want to. And it's just iterating through that and determining who's the highest paid millionaire. And one thing I didn't emphasize properly maybe is like, if I go back to this private get millionaires function, you see here that it's calling this special macro called a read state, which is also part of the ENG-WASM API. And it's basically reading the state to get the millionaire. And in this add millionaire function, we're calling the right state macro and essentially storing the millionaires in there. And you'll see here that it's also using our millionaire struct that I described earlier, that I said is being declared for the purpose of storing things in the state. So that's kind of tying everything together. These read state and write state macros are very important, and it's kind of showing how they're being used here. Moving forward. So now that we wrote a secret contract, we can use again the discovery command to compile it. This is wrapping the compile command of the truffle toolset. And essentially what it's going to do is it's going to compile any secret contract source, which is by convention put in the secret contracts subfolder, and also any smart contract, because secret contracts, it's not shown here, but they're also able to call smart contracts on Ethereum. And this compile command allows to compile both secret contracts and smart contracts that might be included in your project. So discovery compile does this. And discovery migrate is also kind of extending the migrate command of the truffle toolset. And it's actually running the same files that you might be familiar with in truffles, including the deploy contract file. And the deploy contract file simply has some new commands, including the deploy secret contract command that can deploy secret contracts along with your smart contracts. And you can see that in the more elaborate examples where secret contracts call back smart contracts, how the two interact together in deploy commands. But that's kind of the goal here, to be able to deploy both secret contracts and smart contract at once in the right sequence, where you might need to say, give your smart contract addresses to your secret contracts for this type of interaction. You can see examples of that in the repo that was mentioned earlier. So that's how you implement kind of deploying secret contract in this deploy contract file, similar to how you would do it in Truffle. This is just going into more details about it. I'm not going to spend too much time on this, but this is kind of showing how in a deploy contract file you would be able to deploy a secret contract, the sorts of parameters that you have to provide. This is really described in details in the tutorial we're going to link, but that's essentially how it's done in the same deploy file that you would use for your smart contracts. All right, so now we talked about how a secret contract is built and deployed. I'm going to talk about how one would interact with it. And by interacting with it, I mean calling these public functions we described in great detail earlier. So to interact with a secret contract from either a DApp right? Like meaning, I guess meaning. Actually, I don't know what it means. Like so, either interact with secret contracts on the client side, either in the web browser directly, maybe by having your users use like MetaMask, something like this, to call Enigma directly, or using some operator, right? Operator or relayer or something like this that happens to be written in JavaScript, TypeScript, Node.js, something like this. You can use this Enigma.js library that we put together. Essentially, the way it works is the Enigma network has a JSON RPC API that you could call directly, especially if you're using an operator or server application that it's not written in JavaScript. But this Enigma.js library allows you to call that API much more easily and kind of managing the workflow of calling the JSON RPC API for you. It's kind of comparable to what Web3 is to the Ethereum JSON RPC API. And it's a bit more complex than just JSON RPC too. Like the workflow of calling Enigma is more complex than just calling the Enigma JSON RPC API, because some things are also done on the Enigma smart contracts. So some things have to be done in coordination between executing some Ethereum transaction and calling the JSON RPC API of the Enigma network. And Enigma.js, as I said, kind of ties this together and takes care of the workflow for you. So if you're not using JavaScript in your application and you're planning to kind of call the Enigma contract directly or call the JSON RPC API directly, that's a much bigger task. Probably I wouldn't recommend to do that inside of a hackathon. I would recommend just use JavaScript for now, and then use your favorite language implementation for later, once you've proven the concept. So in this Enigma.js library, there are different functions, one of which is compute task. We also have this get result and get task record. I'm going to go over this very fast right now because there's a lot of minutiae involved, and I don't really want to spend another half an hour on this. But this you can learn more about by looking at the examples and tutorials and so forth. So right here I have an example of how to use a compute task.